Okay, so we're just doing problems that reminded us of problems we had done with gravitational force. We've been calculating gravitational force. Let's look at this notes page where we're going to do a side-by-side comparison of the gravitational force and the electrostatic force. Alright, so let's start with the interaction between. So what do objects have that allow them to interact in a gravitational way? Well, of course, it's mass. Really, it is a universal law, so it's the interaction between any two masses, right? You put any two masses in the equation, you can find the gravitational force between them. What for electrostatic force? What do objects have that allow them to interact electrostatically? It's this nebulous quality called charge. This is what I introduced last class, that when objects have charge, they can interact with other objects with charge. That interaction is electrostatic force. But they don't have to intrinsically have charge. They can somehow gain a charge. So let's say it's any two objects with net charge. In this case, net means an imbalance, right? We looked at the atom, and we know that by definition atoms are electrically neutral, a balance of protons and electrons. But I did mention that if you take electrons away or put extra electrons into the atom, now it has a net charge. It's not an atom anymore, it's an ion. And now that it has a net charge, there's an imbalance between protons and electrons, it can interact with other objects that also have a net charge. So it can be an object that intrinsically has charge, like the proton-electron, or it could be some object like the balloon, where you put extra electrons onto it, and it gained a net charge, and then it can interact with other objects with net charge. Let's look at the equations. Since we've just done problems with this, it should be very clear in our minds that the gravitational force, Gmm over r squared, and of course the electrostatic force, Coulomb's law, F sub E equals kq over r squared. You look at them side by side, you just can't help but notice just how similar they are. And so when Coulomb figured out this equation for electrostatic force, the whole physics world was abuzz. They said, wait a second, this equation looks an awful lot like Newton's law of universal gravitation. They're both about forces, both involve some sort of constant. The product of the two objects involved, divided by distance squared, they look an awful lot alike. In fact, remember, there were warnings on these equations. What was the warning on the gravitational force? That, remember, it only works outside. For Coulomb's law, there were two warnings. So one of them was that it only works outside. So again, there's a huge connection here. And so we're going to be really investigating these two forces to see if they're maybe sort of the same thing. Because now scientists started thinking maybe all forces are really the same thing. Maybe there's only one type of force. Wouldn't that be great? If there's only one type of force, there'd just be one equation for force. A cheat sheet would only have one equation on it. That'd be fantastic. So through investigating all different types of forces, they really realized there's only four categories of forces. Only four what we call fundamental interactions. One of them is the gravitational force, also known as weight, and of course here's the equation for that. Another type of fundamental interaction is the electromagnetic force, of which the electrostatic force is part, and soon we'll be getting to magnetism as well. They make up one type of other fundamental interaction. So we have the gravitational force, the electromagnetic force. The other two are nuclear forces. They're called the strong and weak nuclear forces, and we don't really encounter them very much in our everyday lives. The force of gravity we encounter all the time, that's weight. Strong and weak nuclear forces we don't encounter very much, which means everything else must be electromagnetic in nature. So let's think about some of the forces we're used to that we encounter in problems, like, I don't know, the tension force. Remember, tension force is where you're stretching on a material, and what you're really trying to do as you stretch that rope or cord or string is you're trying to rip the atoms away from each other. But those atoms don't like to be ripped away from each other. They build up an electrostatic attraction to them, and that builds up the tension inside. And so tension is really an electromagnetic force on the atomic scale. How about normal force? Right? When you have an object sitting on a surface, what's really happening is that atoms of that object are trying to push away the atoms of the other object, and the atoms of the supporting surface, like your desk or a table, hold each other together with electrostatic forces of attraction. They actually then repel the atoms of the other object through electrostatic repulsion. So the normal force is also an electromagnetic force. The friction force, we talked about how the surfaces sort of bond together with these electrostatic forces of attraction. So friction force is also an electromagnetic force. When you put your hands on an object and push, what's actually happening is that your atoms are getting closer and closer to the atoms of the object, and they're repelling each other when they get to a certain distance. And that is electromagnetic force of repulsion. And so it turns out that no matter how close your atoms get to the other atoms, they're never actually in contact with each other. Your atoms never touch the atoms of the other object. They just get close enough until they repel each other, and you experience that sensation as touch. So in reality, you never actually come into contact with anything. Ever. Yeah, that's the sort of thing that's going to mess with your head as you're trying to fall asleep tonight, right? You're never actually touching anything. Your atoms just get close enough that they repel each other, and you experience that as touch. Yeah, that's crazy, right? Okay, so we're only talking at the atomic scale, though, right? But still, all these forces that are not the force of gravity and these strong and weak nuclear forces are electromagnetic in nature. Those are the only four types of fundamental interactions. Okay, let's continue our investigation here to see other similarities. So let's look at the constant. We just done the problem here for a gravitational force, and we know the constant is capital G is 6.67 times 10 to the 11th Newton meter squared per kilogram squared. Maybe you had to look that up to do that problem. Okay. Electrostatic force, of course, is the K constant. That's 8.99 times 10 to the 9th Newton meter squared per coulomb squared. You see them side by side. Look at the units, right? They both have Newton meter squared. There's replaced kilograms with coulombs, just like replacing mass with charge. Okay, things are looking good. Until you look at the numbers, right? How would you describe this value, 10 to the negative 11th? That's a tiny, tiny number, isn't it, right? How would you describe 10 to the 9th? That is a huge number, right? So, okay, so we're seeing a little bit of a disparity here in the constants involved. But wait a second, let's look at the actual forces. Let's go back to the problem we had done here in number 8, where we found the gravitational force and electrostatic force between the same two objects, the electron and the proton. Let's look at these numbers here, right? Let's look at this force here first. This is 10 to the negative 8th. How would you describe that force? Yeah, that is a tiny force, right? That's not small. That's not large at all, but that makes sense. The electron is a tiny, tiny object. It's going in a tiny, tiny circle. It shouldn't require a very large force to make that happen. What about this gravitational force, 10 to the negative 47th? How would you describe that? Oh yeah, that is ridiculously tiny, right? That is infinitesimal. That is negligible compared to this. So we see for the same two objects, the electrostatic force completely dwarfs the gravitational force. And this can happen in almost all situations. In pretty much all situations, unless you're told otherwise, the gravitational force is pretty much neglected. It's negligible compared to the electrostatic forces of attraction or repulsion. And so we see a really big difference in gravitational force and electrostatic force. Even though the equations look alike, we're starting to see more and more differences. Well, alright, let's take a look at the direction of the force. Alright, so what do masses do to each other when they interact in a gravitational sense? Okay, remember, Newton's law of gravity says they always attract. They're always attractive, right? Masses always attract masses. So no matter how bad your hair is in the morning, you're always attractive in a gravitational sense, okay? I don't know, but otherwise, maybe you want to brush through your hair, right? Maybe you're not seeing anyone, but still, maybe you should look a little better. All right, anyway. The point is that masses always attract other masses. What about for electrostatic force? What do charges do to other charges? Well, we just gone over this last class at the end, our fundamentals, that opposites attract and like charges repel. And so again, we see a major difference. This is happening because there's only one type of mass, and masses attract masses. But this is happening because, remember, there are two different types of charge, the positive and negative. And we made up those words to describe the fact that there are different types of interaction. When they're opposite in charge, they attract. When they're the same, they repel. And so now we're seeing another big difference between the gravitational force and electrostatic force. All right, well, let's look at the graphs. Here we have graphs of the force versus the distance of separation between the objects. And if you recall, we actually did a very similar graph to this. We really did it for lowercase g, the gravitational field, but it certainly still applies here. This is back when we built the tunnel through the Earth. We looked at what happened inside and outside. You'll recall this equation only works outside. So we had to have a dividing line here at the radius of the object. We're separating the distances inside versus the distances outside, where this, of course, is the zero distance, right at the center. So we'll put a little dividing line here. And you might recall, or maybe you want to go back to your notes when we've done this, that when we're inside the Earth, since this equation does apply, we have to do it sort of qualitatively. But what actually happens is we got a linear graph. It was zero at the center. It peaked here at the surface of the Earth, or the surface of whatever object it is that we're talking about. Once we're outside, once we're beyond the radius of the object, now we're outside that surface, well, now we can use this equation. Here, the force goes as 1 over r squared. So you might recall, it was this shape, which is called the inverse square shape. Because y, the force, goes as 1 over x squared, right? The force goes as the inverse of r squared. So it drops off very, very quickly with increasing distance. Let's go over here to the electrostatic force. Now, we're going to build a graph for what's called a conductor. And if you don't quite know what that is, we're going to go over that soon, but just keep that, in the back of your mind. Well, since these two equations look an awful lot alike, and we have the same warning, we know we're going to have the same dividing line, that we're going to have one shape inside, a different shape outside. And outside, well, if the equations have the exact same form, it should be no surprise that's going to be an inverse square again. Of course it is, right? Since force goes as the inverse of r squared, you should have expected that. And then in class, I would say, well, what would you expect to be inside? And so a lot of you would say, well, it's going to be linear inside. And you're not wrong. It is going to be linear inside, but there's going to be a difference. It's not going to be linear with a positive slope. It's actually going to be this, linear with zero slope at 0. It turns out the electrostatic force is exactly 0 everywhere inside a conductor. And so it seems like we have our final nail in the coffin. That there is too much evidence that these two forces are just not the same. While the equations look alike and they have similar warnings and some of the units are the same, there's just so many differences that we can't conclude they're the same thing. But scientists are still trying to get those four fundamental interactions to coalesce into one. And there's been some success to find what we call this grand unifying theory, that all forces are the same. There's been some success linking the electromagnetic force with the weak nuclear force into what's called the electroweak force, but it only happens at very small scales, atomic, nuclear scales. And there's been a little bit of connection between the strong nuclear force and some of the electromagnetic forces as well, but the gravity, it turns out, is the holdout. It seems like no matter what scientists do, they can't get the gravitational force to agree with the other ones. And what's so strange is that in almost all situations, the gravitational force is the weakest of all the four fundamental interactions, which sounds crazy considering we did a whole topic here. We talked about the gravitational force among these huge objects causing the motion of the stars and the planets in the heavens, and those were huge forces causing that to happen. But that's for also very large objects. When you do comparable situations here at the atomic scale, the gravity force almost always loses. And you can show this to yourself by just looking at some object. Like put your textbook on your desk, on your table, whatever it is you're doing your work, and let's see if we can beat the gravitational force. Well, remember, gravitational force is weight, right? So just lift it up. And you should have no problem lifting up your textbook. You just beat the gravitational force. Do it again for yourself. You can prove to yourself no matter what, you can beat the gravitational force. But what about beating the electromagnetic force? Well, we just said that the normal force is electromagnetic. So try now to push your textbook through your desk or your table. Yeah, it's not going to happen, right? Those electrostatic forces of repulsion between the desk atoms and the book atoms are going to win, or at least they're not going to be able to be overcome by you. And this is showing that the gravitational force is much weaker than what the electromagnetic force of normal force can be. And this happens in almost all situations. So there are some scientists who think they figured it out. They're the string theorists. So string theory is this idea that all matter and interactions can be modeled as if it's vibrating strings. Now, we're not saying that they are vibrating strings, but they're saying that the idea of strings vibrating and resonating and connecting and affecting each other can be used to model matter and energy and forces. It's a very odd sort of idea, and there are a lot of issues with string theory, one of which is that to make it work, they have to play around with the dimensions of space. So we know there are three dimensions of space, x, y, z, length, width, height, right? And there is a fourth dimension. If you don't know, that's called time. Okay, so we have four dimensions, the three spatial dimensions and the fourth dimension of time. Well, to make string theory work, they need 11 dimensions. Yeah, so they need 7 extra dimensions, and no one's been successful in explaining where the other 7 dimensions are or what they look like. So there's that. The other issue with string theory is that it's a beautiful theory. It explains things very, very well, but in all of the understanding of it, there's never been a single experiment that verifies string theory. There's not one shred of evidence that it actually works. It's really just a theory. It's a very beautiful theory, and if you were to go into string theory and if string theorists were to be able to explain things and get it to work with actual experiments, there would be Nobel Prizes handed out left and right, which is fantastic. But so far it seems like it doesn't work. Like it explains things, but it doesn't actually have any evidence that it works. Now, to give you a sense, if you ever watched Big Bang Theory, Sheldon Cooper was a string theorist. That gives you a little bit of sense of, some of the strange people who get involved with string theory. And if you go on in physics and you decide to commit your life to string theory, again, if you can get an experiment to prove it, it's almost guaranteed you'll get a Nobel Prize. And don't forget, with Nobel Prizes, you get a speech, and thanks, and of course, the rest, right? So you could possibly become famous and win a Nobel Prize, but you may also commit your entire life to something that just doesn't work. And as you can see, even Sheldon Cooper is judging you.